Below is a list of stars arranged in order of decreasing luminosity, increasing bolometric magnitude. Accurate measurement of stellar luminosities is quite difficult in practice, even when the apparent magnitude is measured accurately, for four reasons. The distance d to the star must be known, to convert apparent to absolute magnitude. Absolute magnitude is the apparent magnitude a star would have if it were 10 parsecs away from the viewer. Since apparent brightness decreases as the square of the distance, i.e. as 1, d2, a small error, e.g. 10%, in determining d implies an error approximately 2 times as large, thus 20%, in luminosity. Stellar distances are only directly measured accurately out to d tilde 1000 Lieutenant YRS. The observed magnitudes must be corrected for the absorption or extinction of intervening interstellar or circumstellar dust and gas. This correction can be enormous and difficult to determine precisely. For example, until accurate infrared observations became possible approximately 50 years ago, the galactic center of the Milky Way was totally obscured to visual observations. The magnitudes at the wavelengths measured must be corrected for those not observed. Absolute bolometric magnitude, which term is redundant, practically speaking, since bolometric magnitudes are nearly always absolute, i.e. corrected for distance, is a measure of the star's luminosity, summing over its emission at all wavelengths, and thus the total amount of energy radiated by a star every second. Bolometric magnitudes can only be estimated by correcting for unobserved portions of the spectrum that have to be modeled, which is always an issue, and often a large correction. The list is dominated by hot blue stars which produce the majority of their energy output in the ultraviolet, but these may not necessarily be the brightest stars at visual wavelengths. A large proportion of stellar systems discovered with very high luminosity have later been found to be binary. Usually, this results in the total system luminosity being reduced and spread among several components. These binaries are common both because the conditions that produce high-mass high-luminosity stars also favor multiple star systems, but also because searchers for highly luminous stars are inevitably biased towards detecting systems with multiple more normal stars combining to appear luminous. Because of all these problems, other references may give very different lists of the most luminous stars, different ordering or different stars altogether. Data on different stars can be of somewhat different reliability, depending on the attention one particular star has received as well as largely differing physical difficulties in analysis. See the Pistol star for an example. The last stars in the list are familiar nearby stars put there for comparison, and not among the most luminous known. It may also interest the reader to know that the Sun is more luminous than approximately 95% of all known stars in the local neighborhood out to, say, a few hundred light-years, due to enormous numbers of somewhat less massive stars that are cooler and often much less luminous. For perspective, the overall range of stellar luminosities runs from dwarfs less than 1/10,000th as luminous as the Sun to supergiants over 1 million times more luminous. Data. This list is currently limited mostly to galactic and Magellanic Cloud objects, but a few stars in other local group galaxies can now be examined in enough detail to determine the luminosities. As of mid-2012 the list is more or less complete for stars down to 1 million times the luminosity of the Sun. Some suspected binaries in this magnitude range are excluded because there is insufficient information about the luminosity of the individual components. Selected fainter stars are also shown for comparison. Despite their extreme luminosity, many of these stars are nevertheless too distant to be observed with the naked eye. Stars that are at least sometimes visible to the unaided eye have their apparent magnitude 6.5 or brighter highlighted in blue. Note that even the most luminous stars are much less luminous than the more luminous persistent extragalactic objects, such as quasars. For example, 3C273 has an average apparent magnitude of 12.8 when observing with a telescope, but an absolute magnitude of -26.7. If this object were 10 parsecs away from Earth, it would appear nearly as bright in the sky as the Sun, apparent magnitude -26.74. This quasar's luminosity is, therefore, about 2 trillion times that of the Sun, or about 100 times that of the total light of average large galaxies like our Milky Way. Note that quasars often vary somewhat in luminosity. In terms of gamma rays, a magnetar type of neutron star called SGR 1806-20 had an extreme burst reach Earth on 27 December 2004. It was the brightest event known to have impacted this planet from an origin outside the Solar System, if these gamma rays were visible, with an absolute magnitude of approximately -29, it would have been brighter than the Sun, as measured by the SWIFT spacecraft. The gamma-ray burst GRB 971214 measured in 1998 was at the time thought to be the most energetic event in the observable universe, with the equivalent energy of several hundred supernovae. Later studies pointed out that the energy was probably the energy of one supernova which had been beamed towards Earth by the geometry of a relativistic jet. See also: Lists of astronomical objects, List of stars, List of largest stars, List of most massive stars, List of hottest stars, List of brightest stars, List of nearest stars, Gamma-ray burst, Quasar, most luminous object.